I see that the number of participants is pretty stable. So I think that we have a really full agenda for today. So I would slowly start this workshop, this meeting. So first of all, welcome everybody to this second workshop organized by the project Synergy Nets, focusing on the policy with the title "Optimizing Grid Stability and Low Carbon Networks." First of all, as I said, this is the second workshop, and it's a pleasure to have you here with us today. My name is Renato Luise. As background, I'm an energy engineer with a PhD on optimization of hydrogen supply chain. I work at the Research Institute in the city of Karlsruhe, Eifer, and I'm the project coordinator of the Synergy Nets project. Today, I will be your host for this event, and I also will be the moderator for the Q&A session that will take place at the end of the presentation that we have prepared for you today. But before start, please, I would like to invite you, in case you are not doing already, to follow our website, SynergyNet. It's just Googling it, you will find pretty easily, or you can see on the screen as well. And basically, on the website, you will find all the latest news about the project, all the tools that have been developed, all the deliverables, the public deliverable, of course, that have been submitted also to European Commission, and also learn more about the overall work that has been done in these last 3 years by all the partners, and that will continue for the next year. Of course, we also have a LinkedIn channel, so please feel free to follow us on LinkedIn as well. So basically, you will receive project updates, participation to future events. So if you want to meet us, and also invitation to this kind of workshop. Just before going into the topic, just few comments. So first of all, this event is being recorded, and basically the recording will be made available on the Euro Heat and Power YouTube channel, which is a partner of us in the project. And you will also find the first policy work and regulatory workshop that already took place. All the presentation that will be presented today will be shared and to the list of registered people as well. So you will receive all the slide pack that will be soon presented. And for what concerns the Q&A session, of course, this is a workshop. So feel free, first of all, to write in the Q&A box. So there is a chat that you can access on the top bar of your screen. But as well, you are really invited to make it as interactive as possible. So please, if you want, just switch on your mic or your camera and make your comments, remark, demand. But please, we would suggest first to let all the presenters introduce their topics, their presentation, and the Q&A will be kept at the end. Of course, you can just start to write your question, so we keep in mind, and if it is let's say, a short answer, we can already have some discussion in the chat. Then, of course, you need to ask for authorization from the Euroheat and Power team by writing in the chat, and that you want to speak, so they will allow you to take word. Before getting into the topic, I always like to give a brief overview of the general topic that will be discussed today, so we can kind of set the tone for this event. As you probably know, peak heat loads are moments of the day in which the energy demand surges quite fast. Normally, we have them taking place in the morning when people are waking up, getting ready for the work, but also during the evening when everyone is coming back home. So attending to these demands is sometimes very big challenge for the utility operators, especially when temperatures are very low, such in this period, for example, like now during winter. So most technologies employed are fossil fuel based because they are, of course, already installed. There are no extra costs. And because most of the cases, natural gas is a cheaper option than renewable alternatives, and they respond faster to the demand surge. Also, because they normally operate for few hours, the cost for operating these technologies tend to be higher, especially when we talk about renewables. So it's a not big surprise that the operators often find it difficult to substitute these technologies in place to more sustainable alternatives, especially during these peaks. So what we need to know, what we aim, we need really to push and incentivize these supply operator to make this change happen, to make it possible. And one of these ways is, of course, through a more supportive policy and regulatory framework. And this is exactly what we plan to do to discuss today. What are these technologies? What are the policies already in place? And what else is in the pipeline? Or, for example, how to ensure that these changes remain economically viable, because it's one, of course, of the most important thing. We will also bring a real case example from our demo site in Ljubljana, and to give a better visualization that changing that is changing that sorry these changes are real possible. So for doing that, I would just like to switch to the next slide, so to the agenda of today. We will have four presentation, five presenters. So we will start with a policy session held by Ruth Kempner from DGNR. Then we will go through an economic session with Edoardo Corsetti from RSE. And then we will have, let's say, a co-presentation held by Ruben Schauer and Yassam Mena from Unicastle and Eifer that will go through the technological session. So they will give us some more technical inputs. Finishing, let's say, the pack of presentation with the demo case presentation, as I already told you, for the Ljubljana demonstrator case with Jure Petkovsek from Energetica Ljubljana. At the end, of course, I will be the moderator of this session. So finally, we will have the Q&A session, and please, I really hope you will active participate to this workshop. Just before starting, a very quick reminder, Ruud, our first speaker, will have we cannot stay until the end of the Q&A session. So since he will have to leave a bit earlier, please, if you have questions directed to him, write them already into the chat, and we will try to answer them during the presentation. So I think that I spoke enough. I'm really looking forward to see also this presentation. So once again, I would, before leaving the floor to Ruth, just a few words on his on him. So he is the deputy head of a unit for energy security and safety within the Directorate General for Energy at the European Commission. Ruth joined the Commission in 2016 and has been responsible for EU's renewables competitiveness, financing, and international cooperation activities since 2020. Ruth also worked on EU's hydrogen strategy as well as industrial competitiveness, including as a cabinet member for Commissioner Kadri Simpson. Before that, Ruud was the power sector transformation strategies analyst at the International Renewable Energy Agency, and he was responsible for the initial development of the IRENA's Global Renewable Energy Roadmap. From 2007 to 2010, Ruud spent 2 years as a research fellow at the Harvard Kennedy School of Government and 2 years as a postdoctoral fellow at the Science Policy Research Unit at the University of Sussex, UK. Ruud received his PhD in chemical engineering at the University of Sydney, Australia, and a Master in Technology and Society from Eindhoven University of Technology in Netherlands. So after this brief introduction of your big career, I would like to leave you the floor, Ruud, and you have roughly 15 minutes for your presentation.
Thank you very much, Renato. And that wasn't a brief introduction. That was quite a long introduction indeed. I could have said, like, I also have a PhD in energy systems modeling. I think that for this session will be more useful. But indeed, I wanted to not talk about the modeling. I leave that up to you. I wanted to give you a sense of kind of the policy environment in which we are today, and that, of course, starts for energy, and especially the word stability, as you mentioned it, with essentially the invasion of Russia into Ukraine, where we really developed this what is called a Repower EU strategy with three angles to it. Now, one of those was kind of diversify away from Russian fossil fuels in total. And this picture is from not last night, the night before, where essentially we finalized that chapter with kind of concrete deadlines for phasing out Russian fossil fuels, gas in this particular case, and then a proposal coming up to do also away with the still remaining oil from Russia early next year. So that kind of chapter is more or less finished. And the reason I'm saying this right now at the moment is because for the other two pillars, so energy efficiency and renewable energy, we've put policies in place and targets in place, but we're really now in a phase of kind of implementation. So how in this energy transition do you then also secure our energy system? And this is actually where your work is coming in. So that's why I thought it would be useful to start off with that and set the scene. Now, I work, as Renato mentioned, in the energy security unit at the moment, where we are kind of rethinking our energy security framework. Now, peak heat was in the title of this presentation, and peak heat has been part of energy security as well, but from a very different timescale. So this is just the data on kind of gas and electricity demand in 2024. And traditionally, we've been looking at kind of peak heat from a seasonal perspective. The dark blue, dark green is essentially our energy gas consumption over a year, and the peak is indeed in the winter. And a lot of the kind of policy and security frameworks are about securing that we have enough gas for that peak, that seasonal winter peak. You also can see in the blue line, the light blue line, that peak is essentially determined by the heating demand in the household sector. So that's the one which is indeed very, very seasonal. And a lot of the policies, like the gas storage policies, the gas supply standards, etc., are there to kind of protect the customers from this seasonal peak demand. Now, the other two lines are the electricity consumption, which you see is much more flat, and then also the gas consumption for electricity, which is also a lot more flat. Now, this is the situation that we have today. It won't change tomorrow, but in a future energy system, we will expect to see a lot more kind of electrification. We will see that energy transition quite radically changing. Now, in my next slide, I have a bit of a video which we have at the entrance of our building. So it essentially says we have a linear system today, and what we want to is a much more circular system, integrated system. And you see in our video, district heating appears first. So this is, I think, quite interesting for your particular workshop. It is one of those elements that start connecting then, which is the blue, the electricity, and the red, which is actually the heat system of the future. And you also can see that indeed we expect this district heating to be kind of a central part of this energy system, connecting heat pumps, so that's electrical heat. It will connect, let's continue with the next slide, heat pumps. It will connect geothermal heat. It will connect residential heat from the, industrial waste heat to deliver those services to the households that we have. So that is indeed this integrated energy system that we are looking at. Now, in such an integrated energy system, we also have to start rethinking our vision on what is peak heat, just like you are doing. We already done this for the electricity sector. So the electricity sector, initially in our security framework, we essentially look at capacity adequacy. Do we have sufficient capacity available to meet peak demand within a given year? So again, that's very long-term perspective. Whereas nowadays we are much more looking at flexibility at a daily level, at a weekly level, and at a monthly level. And this data is from a JRC study that we did a year and a half ago. And it essentially shows kind of how much flexibility we expect to be needed. And this is just for the electricity sector, so it's not for the heating sector, on a daily basis, a weekly basis, and a monthly basis. And for me, the interesting aspect of this is that, like I said, our framework so far is looking at seasonal kind of flexibility. Whereas in a future system, a lot of the flexibility that we are going to need is at a daily level. And in the preparation of this meeting, I already indeed saw kind of the work that is going on in Ljubljana, where indeed you are working on that local daily flexibility, also from a gas perspective. So from that perspective, I think your work is very much welcome in terms of the kind of the broad energy transition that we're working on and the policy challenges that we are facing. Now, this last slide essentially gives you an overview of where I think there are a lot of the different kind of connections to your work, to the policy that we have and that we are looking into. So the top right, the top policies in black are the ones that we have today, and you're probably are hopefully familiar with, because here we have, of course, the Renewable Energy Directive, which is pushing indeed an increasing share of renewable energy in the heating and cooling sector, including through district heating, and also kind of encouraging the use of industrial waste heat. So that helps from a policy perspective to address that issue that Renato just mentioned, to kind of overcome the kind of the fossil fuel consumption still available in the district heating and cooling sector. The element is, of course, the Energy Efficiency Directive, which more looks at the efficiency of district heating and cooling. And there, indeed, efficiency is kind of defined as the unit of heating that is being provided. So again, they're trying to find solutions to kind of shift your demand of heating over time, using the kind of the latent heat possibilities in households to shift that will also help you, of course, with the energy efficiency of that system, especially if you can downscale some of those peaks. A third piece of legislation that I think is going to be important for this particular project as well is the flexibility needs assessments that are now required under the electricity market design. So in April this year, we put forward a methodology that member states have to use to really look at, okay, what are the essentially non-fossil flexibility needs that they have in the energy system, and how are they going to encourage that? And this will also look at kind of different timescales, and here abilities to address flexibility needs through district heating and cooling, or by connecting, for example, heat pumps through district heating and cooling, is of course an important element that can also facilitate some of the solutions that you're looking at. The other element, the other piece of legislation that is already in place is the regulation and the directive on gas and hydrogen markets. And here there are some interesting provisions in the directive that start looking at network planning of, in principle, hydrogen infrastructure. But what it requires there is to have an integrated planning at local level, including district heating systems. So it will ask from kind of local district and local governments to do a much more integrated planning to see, okay, what are the energy needs, what are the energy sources that district heating and cooling systems need into the future, especially with this decarbonization in mind, as well as, of course, the decommissioning question. So what if you are shifting from natural gas to other sources? How are you going to decommissioning that infrastructure, especially taking into account that in some cases that gas might still remain kind of a last resort to deliver the heat to your end consumers, which in most cases, also in the current regulation, are what we call protected customers. So I think these are kind of four pieces of legislation that are all relevant for your specific question. And then we have also three initiatives coming up very soon, which also I think are very important. So on the one hand side, we have the electrification action plan. This plan will not necessarily provide a lot of new regulation, but it will look at kind of the existing legislation that we have, which is, for example, to kind of increase the share of renewable energy in the end use sectors and see how electrification and electrification policies can contribute to that. In this particular case, of course, the use of renewable sources, including heat pumps, to deliver the heat to your households. So either directly or through the district heating and cooling systems will be one of the areas that the electrification action plan will look at. This will coincide with the heating and cooling strategy. The heating and cooling strategy has as its objective really to look at how can we reduce the reliance on fossil fuels for the heating and cooling demand in Europe, whereas 60% of that gas is still used for heating and cooling. So this will also look at, for example, energy efficiency measures beyond electrification itself, and other means to, for example, encourage the industrial waste heat that we talked about previously. And then last but not least, the idea is that this also comes together with the new energy security regulation that we're looking at. Now, the new energy security regulation, as I said before, is going to, in our view, has some new elements to it. One of them, and I've written that down over here, is that we want to look more and more at the demand side to ensure energy security. So traditionally, we've mainly looked at the supply side, not only, but we've mainly looked at supply side and supply side disruptions and how can we counter that. But in this integrated energy system, the end users, of course, are going to play a much more important role, potentially as a supplier, but also through digitalization, they will have much more opportunities to change and shift their energy demand without kind of affecting the services that energy delivers to them. So how to kind of engage in demand response, how to facilitate demand response, how to enable demand response to address energy security is an important element there. And the second one is that we're looking at whether the existing energy security framework that we have today, which is separately for electricity and separately for gas and also separately for oil, whether we have to look at it as a much more integrated approach. Because indeed, district heating and cooling systems already show that the heating, the energy service can potentially be delivered by multiple energy sources at the same time, and electricity and gas and maybe biofuels or geothermal or industrial waste heat. So the question here is, if this is the future system, should we not also look at the energy security regulation in a much more integrated approach? So that's the second angle, which I also think is going to be important for your project, and where some of your kind of solutions and idea might resonate with the future requirements. Then the third one there, of course, is that energy security has always had storage in mind because of this seasonal dimension to it. But of course, district heating and cooling systems can also provide a lot of storage at local level. So how to, and again, enable the possibilities that district heating and cooling systems can deliver in terms of storage and therefore also energy security at local level. So this is a bit of the kind of a broad and quick overview of all the pieces of legislation that are in place and that are coming up. And my main message indeed is that based on what I've seen already before in the introduction, there's a lot of kind of points where your project could be very relevant for us. So I'm very much looking forward to the rest of the presentations as long as I can stay, and of course to continue our discussions into the future. So with that, I'm handing it back to the moderators, and thank you very much for your attention.
Thanks to you, Ruth. Thanks to you. In 15 minutes, you gave us very, very many inputs, and it was really interesting. Also, I would say to see how many topics on the Synergy Nets project are crucial also for you. And I'm always saying it's communication is a key point, and definitely all the results, the outputs, but especially the impacts that we are going to produce at the end of the project will be something that we would really like to share with you. And with those presentation of today, we will try to give a sort of a first inputs, I would say. So, as I said, for the people joined us a bit later, Ruth will not be there for the whole session. So, in case you have already some question for him, please do not hesitate to write them in the chat. And otherwise, I would thanks Ruth again, and I would briefly introduce our next speaker, Edoardo Corsetti from RSE, Research Energetic System. Just translated from the Italian translation, I guess I hope it's the correct one. Edoardo is a senior researcher at RSE, and he participated already in several national and international research projects related to transmission, distribution, and generation of electricity. In the past years, he coordinated various RSE participation in many European projects regarding multi-energy systems. And in particular, he worked on topics such as district heating and system. And he is also currently the a work package leader for the Synergy Nets project. So, Eduardo, please, the floor is yours. You have a quarter of hour for your presentation.
Thank you very much, Renato. Good morning, everyone. So my contribution is related to the flexibility economics, and I will stress how the current regulation is still tailored on the huge power plants, and this represents a drawback, a limit for specific contribution from the distributed generation, in particular from multi-energy systems. So let me come linking to the presentation from Ruth regarding the flexibility needs, which are, as we understood, will increase in the next years, and will stress the system as these needs will be even on a very short term programming. Currently, the flexibility is usually required for solving balancing problem of congestion management, and of course the support to the frequency containment and restoration. So the needs related to the flexibility are maybe concentrated in these aspects. So as I said, in the past, flexibility was essentially provided by huge power plant, and these plants play again a relevant role, and so in particular the role of the plants that are just devoted for the electricity production are when the flexibility is asked for from these systems, have just to modulate the output, the electricity production. So in this respect, remuneration for instance, selling upward flexibility, so increasing the production, just consists in the remuneration arising from the selling extra electricity, so the upward flexibility provided at the price the market fixed for this service. And this remuneration is decreased by the amount of costs related to the extra production. So in particular, for sure, for the gas consumption increasing, as well as the cost for buying downward flexibility. So in case the system, the power system is asking downward flexibility, this implies operators are asking to reduce the production or increase the consumption of electricity. So for huge power plants, this means the contribution to downward flexibility is to reduce the electricity production. And in this case, the plant is in some, let me say, is buying electricity. It is not really a buying process, but it's just a reduction of electricity production. So in this case, so the plant has to pay the cost for the downward flexibility, and the plant can, in case, reduce the costs related to the former gas consumption. Because indeed, in this case, the gas energy is reduced according to the electricity production reduction, and it is also possible for this kind of plant to reduce the costs related to the former transmission and charging cost components that the buying of the gas was paid during the programming session. So this highlight the structure of cost components. So if energy is sold at a price fixed by the market, the day-ahead market, intraday market, and so on. So the cost for those entities that consumes the energy is related to the price, to the cost, to the component of price of energy, but also to the tariff for transmission, distribution, and dispatching, as also to the charging cost due to the incentivized, several policy for incentives that are foreseen in the regulation. So that's bringing in action a complexity, especially for the flexibility downward provision. And let me come to the multi-energy system, to the distributed generation and multi-energy system that in many cases are represented by district heating and cooling, as discussed during the introduction. So in this case, the provision of flexibility can be really an opportunity for the multi-energy system from one side, and for the system, for the power system, because these systems are in many cases reliable entities operating on the grid, and are able to provide a wide set of services which in this case are highlighted by this graph where the different where for the a daily programming activity of the third district heating power plant, a lot of possible products can be provided. So in this picture are highlighted the bids for FCR, AFRR, MFRR in upward and downward congestion management for TSO and DSO products. So how, if this plant is able to provide a so huge amount of flexibility, and this flexibility can be compliant to a number of several different services, ancillary services, how this plant can provide this flexibility. So the message, so sorry, coming back. In this case, really, the point is not just to modulate the electricity production or consumption by the plant. It's in many cases it's a much more complex action that requires the balancing of different systems in order not to affect the demand satisfaction. Sorry. So let me focus on one of the several ancillary services provided by the plant, and I propose the detail regarding the AFRR ancillary service, which is represented in the graph at in the slide. So in this case, for each hour, several devices are involved in the flexibility in the AFRR provision. And so the different bars highlighted these contributions, and in particular the blue bars represent the contribution from several CHP gas engines in the specific plant taking into account. And instead of the green bars represent the contribution from the electric boiler. Then in this case, CHP are electricity generator, while the electric boiler is an electricity consumer. Then when they provide flexibility, they are operating in the opposite way. So in the case of generator, electricity generator, increasing flexibility means to increase the electricity production, while in case of the electric boiler, increase the flexibility provision means to reduce the consumption of the electric boiler. And this impacts on the main service the plant is devoted to, so the production of heat. And in the discussion, let me go into a brief detail about the behavior of the plant. So in this case, I just take into account the AFRR ancillary product in the upward mode. In this case, with the contribution of the plant to the flexibility provision, for instance, in the time instant 4 and time instant 5, with respect to the each carrier, is completely balanced because the contribution for the AFRR provision is provided by the CHP from one side and the electric boiler from the other side. So the AFRR in this case don't impact on the heat production, because the contribution of the devices can be operated keeping the balance safe. Instead of in the at time 20, the contribution of the for the AFRR provision provided by ASHP, so the blue bar, cannot be compensated by the electric boiler, which is not involved in this case in the provision. And in this case, we have to provide with another device. In this case, the orange bar represents the contribution of a gas boiler. And this is the core of the problem with the multi-energy system in provision of flexibility, because we have, in many cases, when the flexibility is provided, we have to rearrange the schedule of the different systems in order not to affect, as I said, the demand satisfaction. So this is the representation of the downward provision. And in this case, we are adopting for balancing the heat carrier the contribution from the thermal energy storage represented by the pink bars. And in the same way, we have to compensate the increasing or decreasing of the electricity production with some other devices in order not to affect the demand. All this, if on the heat carrier, the balance is, let me say, concentrated within the plant. In case we need extra resources, in particular gas, we need to provide some bids on the market in order to acquire or sell gas amount to increase, to sustain the electricity production or to reducing the electricity production. And in these two graphs, and I don't go into the details because, but I've just stressed the point that the green dashed lines represent the extra gas or gas consumption reduction that are related to the balancing of the heat carrier in particular in this case. So the message at the end is once a multi-energy system is asked to provide flexibility for this kind of system, the point is there are a lot of complex actions that must be fulfilled in order to maintain the satisfaction of the main goal they are devoted to, and at the same time the provision of the flexibility itself. And in these actions, there are technical matters. So as we said, we have to combine the contribution from different type of systems, different type of devices in order not to affect the demand and to try to the reduction of the cost. But at the same time, we have to interact with the different markets, because once we are the ancillary service is activated, just in this at this moment, we know that we need to reduce the gas consumption and to increase the gas consumption. And this in particular, these processes are not completely kept by the market organization in many cases. So the discussion about the different points regarding the regulation, the current limit in regulation are just reported in these two slides. So where we identify the challenges and market regulation in this one. So just let me mention the market access threshold, the data and telemetry knowledge, the tariff structures, the cross-sector coordination gaps between, in particular, electricity and gas and heat, and about the policy uncertainty. So the policy in these last years changed a lot of time, and this not introduced in this procure uncertainty. So the potential solutions are listed in these slides, and disregard how to reduce the market barrier access, how to the standardization, to standardize data framework, reform the tariff design in order to keep into account the complexity of some contributions, some specific subject when contribute to the flexibility provision. And so the mandate to integrate the planning, so the coordination about among the different system operators. And so that's are more or less the main messages that I borrowed from the project, from Synergy outcomes, and that's it from my side. And thank you very much for your attention.
But thanks to you, Eduardo. Indeed, it was really interesting to see all these insights and really from the Italian demo case, so some real value how to handle, let's say, this flexibility for the upward and downward, especially. But maybe we'll keep these comments and questions for later, since we have already time for our next presentation, maybe. So I think, yes, exactly. We can go now to the technical part. So to our developers in the project, which are represented today by Yasant and Ruben. So Ruben, he's a mechanical engineer with over 15 years of experience specializing in energy system analysis, techno-economic feasibility studies, and municipal energy infrastructures. Ruben currently leads the Distribution Network Planning Group at the Fraunhofer Institute for Energy Economics and Energy System Technology, and also a parallel group of the same name at the University of Kassel, Department of Sustainable Electricity Energy Systems. And Ruben, as Eduardo, is also a work package leader in the Synergy Net project, and he's working for Unikassel. Yasant is working for AFER. He's he's an engineer in sustainable energy and software developer, and he's working at AFER since 2 years. He's working on different topics on energy system modeling, especially in the modeling of heating systems in the scope of the Synergy Nets project. So you both have a combined presentation, so I would leave you the floor. I guess Ruben is gonna start, but please go ahead. Ruben, if you are talking, we are not hearing you.
Okay, is it working?
Definitely
All right.
better.
Thanks for the introduction. Sometimes technical equipment has to be restarted. So first of all, I want to give an overview about the general issue. Please click to the next slide. All right. So like in an electricity grid, there are also varying levels of heat demand during the day. So in the morning, in residential areas, the heating systems are turned up either automatically or manually, or in the industrial sector, technical processes are starting. And on the right side, we see in an example of this, we have a load curve of a heating network from one of our consortium partners as a fat blue line. And we see 3 main peaks in the morning, in the noon, and in the evening hours. And we also see the supply by different heat sources that are used to fulfill those needs. And of course, the energy efficient heat generators like heat pumps or CHP must run as continuously as possible, because they are also the most expensive ones. So the closer we come with the full load hours to the 8,760 hours a year has, the better. So as we can see, the base load is delivered by the CHP. And it is supported by the heat pumps in the noon hours or in the day hours. And then we also have a thermal storage that is charged during the night hours. We see that the the load is below that constant line of the CHP. So there it is loaded, and in the daytimes the thermal storage is emptied or is discharged. And everything else, the gap between those technologies I mentioned, that is delivered by just gas boilers, since this technology is cheap to acquire and also to maintain. And that is the core of the problem. So these big fat yellow peaks are, of course, very fossil, and on the way to decarbonize the heat distribution DHC, we need to get rid of those peaks delivered by the gas boilers. Okay. I think I can click myself, but that didn't work. So please, I want the next slide. Now I can do it. All right. So the solution approaches, since I only want to talk 5 or 6 minutes, so I broke them down very simply, are to ensure decarbonized peak load coverage. That can be, of course, there is not one technology that can meet all the demands, but it has to be a mixture. Here we see a little residential heat pump, but of course it's a symbol for large-scale heat pumps that can be used, and they will become cheaper because we have a technical process, and we also will get the scale of economy that makes the big heat pumps cheaper, so they maybe can be also used for peak. Of course, electro boilers, that's something we saw in the last slide. There was also a color for electro boiler, which wasn't used in the day. So electro boilers are also a low investment costs technology that in a decarbonized electricity grid can provide heat when there's an overflow of electric power. Biomass is tempting, like waste wood or something. It is tempting, but it's also a limited resource that cannot be used all over Europe. And additionally, there are also some logistical challenges. So in my city, there's going to be built a biomass heat plant, and approximately 4 lorries have to pass a residential area a day, and there were many protests. So it's not all biomass is not the solution that helps us here in a big scale. And of course, we heard that there's also industrial waste that can be used, and that, of course, that would be a smart way. But of course, you need a reliable partnership, and of course, high temperature levels are also desirable that are not always available. So then also we have short-term thermal storages, like in the example picture or in the example on the slide before that. They are good to buffer peaks, and since heat can be stored better than electric power, it's not a very complicated technology, not a complicated process, well established and cheap to acquire, but obviously not for free, and also not the solution for everything. But it's good to get the peaks covered at the plant site. But the most elegant solution would be like in the little symbol picture, to smoothen out the peaks directly at the consumer level, and there we will learn something about that in the case study we will hear with Jure, and he will tell a little bit more about that. So what would be helpful from the politics, and also what would be needed on the market level? So to enable district heating network operators worldwide to meet these challenges I mentioned, there are at least 3 approaches. So the public funding can help to tackle the costs for developing, planning, or investment, and making the solutions cheaper on a long run. Of course, CO2 prices can bring down the gap a little bit between low carbon solutions and the fossil ones. And of course, on the way to an interconnected multi-energy system, we need flexible consumers and prosumers that use the energy when there's plenty and save energy when there's a shortage. And for that, we need a regulatory and market framework that helps supporting it. There, we are making progress compared to the last 10 or 20 years, but there's still a long way to go. And to plan the best way how to operate a multi-energy system, we need planning tools that are capable of processing all the data we use for that. And on this slide, I want to briefly present Panda Prosumer as an open source Python-based tool that was developed within Synergy Nuts. And it's able to simulate sector coupling between molecular district heating and power grids, as symbolized in this little picture here. And here as an example, we have the CHP that takes from the gas grid, provides for the district heating grid and also for the power grid. And that is the key solution. And of course, it helps to model the energy systems and the multi-energy systems, but of course it's important to give more input, like Eduardo just showed the market situations, weather conditions, flexibility, possibilities, and all of this can be processed within Panda Prosumer, and it is capable of eating up grid models as breakfast. So we have some converters that can convert electric grids into Panda Power, as you can see here on the right corner. And then we can also process the data of every grid data or grid model we can get. So, and since there's not enough time to go deeper into the tool and the possibilities there are here's a little simulation from a minimal example, but I think now is the time that Hyacinth can show us a little bit how the tool can be used, a little cutout.
Thank you, Ruben. So on my side, I will try to share my screen. I sent a request, so declined by the host. Evan or Marietta, could you? The host isn't allowing sharing for this meeting, I see in my side. No, I cannot share.
I think Marietta should allow you to share the screen.
I have control of the slide, yes, but I wanted to share the screen.
Yeah, since this is a live demonstration of the tool, there are, of course, everything that happens live can be troublesome.
But
maybe
maybe
see the host isn't allowing sharing for this meeting. I try. Something else. No, I try again in Denver. Oh, good. So you should be able to see now.
Yes.
So thank you, Ruben, who introduced you. So the Panda prosumer that was already introduced during the previous webinar last spring of Synergy.net. So if you want more information, you can either check out the GitHub that is available open source, or go check the last webinar that is available on YouTube. And I will demo a user interface that is building on top of the Panda tools. that will allow a user to use this tool without going into the code and the technicity of Python. So I can show you, I have here study, and in this study, so it's a web application on which you can see the detail of the study I created. So this is a very small sample of the Milan use case, where you can see I have my district heating network here. For example, this one is a pipe, and I can see the detail of my pipe. With, for example, here I have the information of the diameter of the pipe, etc. I have also the lines, the electrical distribution lines. I have the Canavese power plant, which is the heat supplier of the district heating network. And I have here model only 4 substations in this network. You can easily add some new layers if you want and specify whether it defines the pipe, the production, heat production facility, the substation, the lines. And I can also specify, if I go in pipes edit layer, I can specify, for example, in this case, the internal diameter of my pipe will not be a constant value, but it will be the property, so the attribute diameters that come from my file. The length as well, I have a property, which is the length. I can also specify, in the case, for example, the heat transfer coefficient, which is needed for the calculation. In this case, I don't have any data that fits this requirement. So I can just set a constant value that I can use for all the pipes. So this is for the pipes network. And then I can also add some data, so some time series. Here you see I created 2 different time series, one that is the production facilities data and one for the substations. If I want, I can add some new ones with CSV or Excel format. If I check, for example, the production data, you can see I have a temperature, I have an electricity price, and in the demand, I have my demand profile, which looks like that. So with a peak demand at some point, which is obviously some fake data that I made for illustration. Can go back here. And now if I click, for example, the Canavese power plant, I can specify which technologies are within this plant. So now I have this molded builder in which I see on the left side here, all the technologies that are available in Panda prosumer. So in Panda prosumer, you have a lot of technologies, for example, heat pump, that as Ruben showed, we can connect the different energy carrier together. So the heat pump will connect the electricity, consume electricity, and produce some heat in the fluid network. I see also here my prod data, my demand data, so my time series. And if I take the production data, I will see the 2 columns from my data, which is the ambient temperature and the electricity price. And here, for example, I can connect the ambient temperature to the evaporator temperature of the heat pump. Then I could connect the condenser of the heat pump to the connection, the return here, the connection to the district heating network. And then I have the electrical power of the condenser, of the compressor, sorry, that I can connect to the electrical connection that will connect it to the Panda power, so the distribution grid model. And like that, I can create what we call a prosumer that will be stored in this Canavese power plant. Now to be a bit quicker, I created another study in which I have a bit more complex system here. Load ones. Well, you can see I have a heat pump, but I also introduces an electric boiler and a heat storage. And this heat storage will be useful because I have my heat pump will be only, if you click on the heat pump, you can see the attributes of the model, and you can see that the maximum power is 200 kilowatts, which will not be enough for the peak load that I have. That's why I will need this heat storage. If now I go in simulation, now I could run a simulation of my system here, with, for example, my new simulation, and it will run on the server. Now, if I go in the list of simulations, I will see that this new one is running, but it will take about 30 seconds. So to not have to wait, I will go in the previous one to show you the results. And here you can see the result. I have, for example, my Canavese power plant. First, I see the network, so the distribution, the power and distribution network, the pipes, and the prosumer, in which I have the Canavese, so my plant, in which I have, for example, the heat pump. And the heat pump, I can see that the profile of the heat pump. So I see all the results of the model. You can see, for example, in blue is the power of the condenser that is so sent directly to the network. You can see that at this point, during my heat load, it will reach actually the 200 kilowatt maximum power in green. And so during this time, the heat pump will not be enough to cover the demand. I can check also the electric boiler and the storage. And basically what you can see is that at the beginning, the electric boiler will charge the storage, and during the heat load, the storage will unload in order to supply what the heat pump cannot supply. I think I'm reaching already the end of my time, so I will just show that there is also a button to download the results, in which I can directly get a zip file that will contain all the results. So for example, if I go to prosumer, I will see the Canavese result I show you in the same format. So to be able to extract the data and do something with them. Yeah, I think that's all I can show during my time. So thank you for listening.
Thanks to you, Yasante. I mean, I know the complexity of the model you both have developed, so really not easy to stick to the time, but thanks a lot for this quick presentation, and of course to all the participants that would be interested in knowing more. We have already published 3 different webinars for the different Panda tools, and it's everything open source, which means that is if you go to our website of Synergy Nets, you will have the links that will connect to the library and to also to the explanation of every single model. So now, since we are running a bit out of time, I would like to directly introduce our new speaker, Jure, who is a research and developer project manager at Energetica Ljubljana, which is a local utility managing a district heating network, a gas distribution network, large CHP, and electricity supply in Ljubljana. Jure's focus is on the electricity load and the gas load forecasting systems. And at his previous positions, he got experience from coordinating the development of the fuel cell power plant, commissioning the hydropower plants, and developing heat exchangers. So Jure will give us a concrete sample of the Ljubljana case study. So Jure, please, the floor is yours.
Thank you, Renata. So, let's see. Yes, may I ask, can you see my pointer or not during the presentation?
No, but usually you could. No.
Okay, just to make sure that people don't see this. Okay, so thanks, Renato, again. Let's see how the designing and implementation of the heat demand response controller looks in the district heating system of Ljubljana. Let's first take a quick glance of the whole presentation. Let's first see who we are in Energetica Ljubljana, what infrastructure we are operating, what challenges we are facing when doing that, what is the solution concept, which was then implemented in the Synergy Net, and the required infrastructure upgrades with some preliminary results we can already present at this time point. So, excuse me, there's a bit of a delay. Yes. So Energetica Ljubljana, we are the operator of the district heating system in the capital city of Ljubljana, Slovenia. we are providing more than 1 terawatt-hour of heat per year for our end users. This corresponds to about 60,000 households. At the same time, we are also the operator of the distribution system for the gas network and also the gas supplier for some of the end users in our network. We are operating 2 large CHPs, where also the electricity is a side product. So this means that we are also the balance responsible party and at the electricity network and the electricity supplier. So here I can already refer to some questions we received in the chat. Someone was asking about this economics between heat and electricity. So in Energetica Ljubljana, our mission is to supply heat to Ljubljana, to keep Ljubljana warm. This means that the electricity in our case is considered strictly as a side product. So this is also how it is treated. But of course, to some electricity utilities, of course, the thing is the other way around. So here we can see 2 large CHPs we are operating to feed heat into our district heating system. The first one is the PPA toll, which has been recently commissioned and it's operating on gas. It can have total heat capacity of 380 megawatts and 155 megawatts of electricity. And what can be seen in the image on the left-hand side, you can see a big cylinder. It's a heat storage tank with quite high capacity, which is enough to provide heat to Ljubljana for 8 hours without any operation of the CHPs. So it's also a sort of a redundancy or plan B if something goes wrong. On the right-hand side, we can see the image of another unit. It's called TOSH. It is more or less peaking and redundancy unit with the heat capacity 230 megawatts and 7 megawatts of electricity. So what are the challenges we are facing when operating our district heating system? We have seen a sort of this image already a couple of times this day, I guess. So it represents the total heat load or heat demand from our district heating network. We can see below that it represents the heat loads from a typical winter day from midnight to midnight. So within the day, we can see that we have a certain amount of base load, which is taken from our system all the time. And then in particular at 6 o'clock and in the afternoon hours, we have 2 very pronounced peaks where we have to satisfy an increased demand for the heat load. So basically, these peaks are created mostly by the end user behavior. Everybody wants to have these offices, apartments, other buildings warm at 6, 7 o'clock in the morning when people start working or get up in the apartments. So the biggest challenge here for us is how to supply this heat to the end user. So to some distant location away from our CHP. So we are solving this with 2 possible solutions. One is to increase the water flow through the pipelines, which means that there are increased pumping costs. Or another solution is to increase the hot water temperature in the pipeline, which means increased pipeline heat losses. So the solution we desire is somewhat presented in the next diagram. We can see an old diagram we have seen before with the gray line. So we would like to load shift the morning peak into night hours and also into the afternoon hours, which would have 2 effects. The first one, we have an increased baseload heat production, which results in total higher efficiency and less equipment wear of our CHPs. And on another hand, if we have reduced use of peaking sources, this means lower emissions because peaking sources are usually less efficient and have higher ramp rates. So what is the solution concept to implement the heat demand response controller? The idea is that all the heat stations, at least the ones participating in the project, need to be upgraded so that they are able to communicate with the central heat demand response controller, which is also called the virtual heat plant. So the stations need to be upgraded so that they are able to receive commands from the central controller to increase or reduce the heat taken from our district heating network. The first task we had to do within the project was contracting the end users. So we have signed 47 contracts with end users in Ljubljana district heating network. We did our best to collect a representative sample of our district heating network. So we wanted to have different users like residential users, businesses, offices, kindergartens, schools, and we also have a medical center and one cultural institution in order to have a really good sample of the full Ljubljana network. So we did our best to spend the whole budget dedicated for the equipment, and this was enough to get a sample of about 1% of our total network in Ljubljana. Then the next task was, as mentioned, to upgrade the heat stations. So you can imagine the heat stations are usually some dusty engines somewhere in some forgotten places in the basement. We can see an image of controllers of such heat station on the left-hand side below. So we can see 3 devices which were added to the heat station. One is a new controller within the electrical cabinet. And then on the right below, there is a smart heat meter, and above there is a communicator which is able to communicate with the central heat demand response controller through radio or GSM connection. This connection is established via some respective providers' clouds. We are using 4 clouds, and here in this image, the Danfoss cloud is presented, which enables communication with the Danfoss controller and the central heat demand response controller. And at the end, the last slide, we can show some preliminary results we have achieved with operating our heat demand response controller. These results were taken in 2 consecutive days. The line with the higher peak is the one taken on a reference day, which means business as usual. We can see that there is an increased heat demand at 5:00 a.m. and then it drops a bit, and then at 6 a.m. we have a really sharp increase in the heat load. These lines represent the total heat demand of the 47 heat stations which are taking part in the project. So the next day we have implemented our demand response controller, and we used a very simple and, let's say, quite non-invasive solution. So instead of opening the valves within 1 minute at 6 a.m., we just extended this period over 1 hour. So instead of opening the valve at 6 a.m., we started opening the valves at 5:30 and ended this at 6:30. So there was absolutely no impact on the end user's comfort. No building was switched off, and we have already achieved with such a simple solution quite promising results. So this is what we can show now. We are working on further solutions also to temporarily switch off some heat stations, but the project is still running and we are still doing this. So there is not much yet ready to present. So this is pretty much it. Thank you for your attention, and also to the Commission for co-financing our activities.
Thanks to you, Jure. Very, very clear presentation, and maybe, I mean, we can also tell the people a bit they are not very still aware about the project that right now in this period we are running the test and trying to optimize, simulate and optimize the system. So, like you already show us, there are the first, let's say, minor or you call it easier, but still a modification that are improving the system, the energy efficiency without, let's say, how to say, without that the clients are affected by that, which is basically also one of our scope. And I'm really looking forward for the next solution that will come out. And also, thank you very much for addressing already the first question of Federico Meazzi. So maybe since we have a few questions already as well, I would just go through them and maybe ask to the reference people to answer because we have two questions concerning the modeling part. I mean, first of all, if Eduardo first, maybe you want to add something on the from the question of Federico, or otherwise.
I read the question. The point is exactly as Jure has just showed. The point is the heat demand cannot be uh, cannot be cannot be satisfied, must be satisfied at any rate. So even in case we are moduling the demand, the heat provision, and so we are asking to the demand let me say in some sense a flexibility. This flexibility means that if we provide more power, more heat power, then we have to decrease this heat power in the next time slot. And even the reverse is much more complicated because we cannot start decreasing the heat production for lowering then the heat demand, because in this case we can incur in a discomfort situation that are really complicated. Then in principle the point is the provision of flexibility must always be performed in satisfying the comfort level of the demand. That's my point.
Thanks. I'm seeing many questions pumping up, so I would go to the part to our modelers, so to Yasan and Ruben, because we have a first question from Moritz. How is the control represented in Panda Presumer? And then yeah.
Yes, I can answer this one. If I understand correctly the question, I say I can answer by talking about two features in the Panda prosumer, which is first, you can specify the merit orders of the different bricks. So for example, in the example I show, I didn't show it, but I can specify that I want to use in priority the heat pump, and then with the higher merit order, the storage. And also there is a special brick that we call the supervisor that I use. In this case, if you remember, I had a time series with the electricity price, and I use it to create a simple logic that if the electricity price is above a threshold, I will shut down the electric boiler to not use too much electricity when it's expensive. There's this kind of control that we can do with the library.
Okay, thanks a lot. And also concerning the time step specification, because Thomas commented that it was a pretty high, I would say 1 hour, but it probably depends on the inputs. We can also go down, but I let you.
Yes, exactly. We can go down if you want. In this case, it's true. I had a 1 hour. I simulated 48 hours with a 1 hour time step, but we can go down. For example, in the case of the Paris demonstrators that I also in the Synagenet project, I have, I think, a 5 minutes resolution in my data. So I use the same resolution in the modeling and it still work fine with not too long simulation time for modeling, for simulating several weeks of data. And there are some models that may slow down a bit. For example, the stratified storage is probably the slowest to calculate, but it still work with the lowest resolution.
I see. But I mean, what we can say then is that until now in the project, we work at the minimum time step at 5 minutes, but Thomas is also challenging us. So a resolution of seconds, which means that probably we will also try this kind of solution, and we will see in the next step of the project. But I saw that he switched on his camera. So maybe Thomas, you want to add a comment?
Yes. So if you look at the thermal side only, then this slow time scales may be quite okay. But if you think about charging cars, if you think about batteries that you might have in homes, and you want to coordinate all of them across all sectors, then 5 minutes, particularly with the dynamics of a small system, which does not average that much, could be a challenge. Let's not discuss that at length here. Maybe Renato will have a separate meeting as well.
Definitely, we already were in exchange, so we can also continue this really interesting discussion on a separate meeting. And I would go to Matthias also, because he's asking, in order to be allowed to set up installations in end user buildings, do you have to have a contact with each individual end user? And what does the end user gain from providing this flexibility? That was actually also my question for you. So maybe some feedback or.
Yes, thanks for the question. It's very relevant. Probably it's not. I cannot provide the universal answer. I can provide an answer which is referring to Ljubljana case. So in Ljubljana case, the end users are the owners of their heat stations. So everything which is done there must be in a sort of agreement made with them. And it was quite a big effort to sign, to get this permission to do this. So we signed contracts with them. Their participation was on a voluntary basis. And what we decided to do is to offer free of charge maintenance of the heat stations for the time of the project. This was the solution which was actually benefit for both sides. End users got the cost reduction on their monthly bills. And at the same time, the Energetica made sure that nobody else is doing any changes on the heat stations in this time. So the new equipment which was installed would not be disconnected and so forth. And also the equipment which was installed is considered the computer equipment because it's an IT equipment, and it will be left to the end users when the project ends. So it will become their ownership. And I can mention also this, that when getting residential end users, we did a lot of effort to get these end users, whereas we had also a strong support of the municipality of Ljubljana, which is actually the owner of Energetica Ljubljana, and they helped a lot when getting the public buildings like offices, kindergartens, schools, medical centers, cultural institutions. This was all made in agreement with the municipality of Ljubljana. So also great thanks to them.
Thanks a lot, Jure. And maybe there is a last quick question, I would say, because Moritz is asking, before the optimization, the night shutdown modus of all controllers ended at 6 a.m.?
It again depends on the end user, because the controller is in fact owned by the end user, but the majority of the controllers go from the nighttime to the daytime regime at 6 a.m. It's not the case at all heat stations. Some stations do that at 5 a.m., some stations at 7 a.m., but the big majority does this at 6 a.m. And also these schedules depend on the day type. So the offices do not heat up on Saturdays, Sundays, and then they start heating a bit earlier on Monday. So the majority of tests we are doing is between Tuesday and Friday, because this is these regimes are comparable. This is what I can say from this regard. Yeah.
Thanks a lot. Indeed, you pointed another topic that also maybe we could mention for our next workshop and so on, but also this representative day. So the reference day can be a working day, it can be a weekend, then we have the seasonality and so on. So there would be many case studies to show, but unfortunately we were also a bit limited in time. But I would say that this session, this workshop, first of all, I would really thanks to all the participants, all the speakers, the presenter, the organizers, and also the really the people, the audience. I really love when we are interactive and active exchanges, since for us this is really the goal, to get feedbacks, to try to see if we are missing something, to try to get other point of view. And we saw already with Ruud, which explained us all the regulatory framework, and try in few words also to show us how also the final user could be play an interactive let's say role as co-suppliers. At the same time, the importance also for us as project, or the cruciality, the really central point of district heating and cooling networks, as well as flexibility. The flexibility that also is kind of getting remunerated, as Eduardo briefly showed us, in the upward and downward flexibility. And we saw also a bit from a technical point of view how models could support us. And we had this presentation and showcase of the Milano simulation with Panda Prosumer. And in the end, we had also the real application of the Slovenian case study. So we also had the possibility to show 2 of the 3 demo sites. So it was really interesting, and I hope that the audience really enjoy it. We already are 3 minutes out of time, but I see a last question to the topic of flexibility. Is there something like a priority? To the topic of flexibility, is there something like a priority system for flexibility, so that system like electrolyzer come first to consume excess energy, or renewable come first to feed energy into the grid? I
Yeah,
don't.
it's, in principle, for instance, the graph that I showed represented a complex situation where in each ancillary service can be provided in principle by a pool of technologies, and the schedule of these technologies can be decided online once the ancillary service is activated. Then at that time, in case if we have time to start an optimization, we can quickly arrange a schedule, the best schedule that can be provided in order to satisfy from one side the ancillary service, and from the other side the other matter the system is involved in. So in principle, that it is possible. So that's my answer.
Thanks a lot for this last minute question, Eduardo. And well, I would say a big thank you again. Don't forget to follow us on the social media, on LinkedIn. Just Google for Synergy Nets. You will also see our website from where you can subscribe to our newsletter to get always the latest news on the project, and also get invitation to workshops like today or webinars. And you will also access to the webinars that already took place and have been recorded and made available for the community. A big thank you again, and I wish all of you a good day. Bye bye.
Thank you.
Goodbye,
Thank you.
everyone.
Bye bye.